Hello and welcome to the next in the short series of videos about noise. This time the subject is noise colours, what we mean when we talk about pink or blue or brown noise. Well, just like light, noise contains different amounts of energy at different frequencies. Light also contains different frequencies. White light, as you can tell when you do the classic experiment of passing it through a prism, is divided into a set of colours from red at the low frequency end of the spectrum up to violet at the high frequency end of the spectrum. Noise behaves in a very analogous way. White noise contains all of the possible frequencies that we're interested in. But not all noise is white. This plot here is similar to one we've seen before. If you look at the scale on the y-axis, you'll see that at almost all of the frequencies, the noise has a value of minus 29 dBs. It looks ragged purely because the scale on the y-axis is so small, but every single value there is within half a dB of minus 29 dBs. Effectively, that is a flat spectrum. Same amount of energy in every single one of the frequency ranges. That is what we refer to as white noise. This noise, however, is not white. Look at the scale on the y-axis. It goes from about minus 18 dB at the very low frequency end down to around minus 47 dB. That's a range of over 30 dBs or a factor of 1,000. At lower frequencies, this noise has considerably more power than at the higher frequency ranges. This is noise that we refer to as pink noise, because if it were light, we would have more energy at the red end of the spectrum, less energy at the blue and violet end of the spectrum, and the light would appear to be of a pink colour. Pink noise, however, is not just any noise which has a greater amount of power at the lower frequency end. It is a specific type of noise. If we plot the same data but on a logarithmic x-axis here, so we're plotting it against the log of frequency, then you'll see that for this particular type of noise, the power decays in a straight line as the frequency gets higher. We can do a little bit of maths on that and characterize that curve more accurately. Consider if the power spectral density, that's the amount of power in 1 Hertz of the noise, was related to the frequency in such a way that it was proportional to 1 over the frequency to the power of a constant, which I'll call alpha. If I write the constant of proportionality as k, that just becomes the power spectral density is equal to k divided by f, the frequency, to the power of alpha. Take the logarithms of both sides of that, and we'd get 10 log of the power spectral density is equal to 10 log of k minus 10 log of f to the power of alpha. Using the useful property of logarithms, that log of x to the power of y is equal to y times log x. We could write this as 10 log 10 of the power spectral density is 10 log 10 k, that's just a constant, minus 10 times alpha log of frequency. And this is the equation of a straight line. The gradient of the straight line is minus 10 alpha. Now, if we go back and have a look at this plot on the curve here, we'll see that at 100 Hertz, we're getting about minus 23 dBs. And at 1 kilohertz here, we're down at about well, about minus 33 dBs. Now, at 100 Hertz, log of f is 2. At 1 kilohertz, log of f is 3. So we have 2 points on our graph here. That means we can work out the gradient. The gradient would be, in this case, minus 23 minus 33 divided by 2 minus 3. That's the gradient. That's the difference in the y coordinates of these 2 points divided by the difference in the x coordinates of these 2 points. Well, that is 10 over minus 1, so that's minus 10. That's the gradient of this graph here. The theory predicts that the gradient should be that. Therefore, we can deduce that alpha is equal to 1. And what we have here is a type of noise in which the power spectral density is proportional to 1 over the frequency. I've called it pink noise here. It is often called pink noise, but there is another term for it, another name for it, and it's often called 1 over f noise. And it happens quite a lot in a lot of different physical situations. It's a very common type of noise. This is what it looks like in the time domain. White noise looks like this. Very rapidly changing noise, and it can take any value. Pink noise looks like this. It moves rather more slowly between its minimum values and its maximum values. There is some what looks like very high frequency noise, but there's low frequency movements as well, quite slow movements up and down. They are very noticeable, and they are a result of this noise having more power at these low frequencies. There is another type of noise that has even more of its power at very low frequencies and even less at very high frequencies, and it's called brown noise, and it looks like this. Somewhat confusingly, brown noise is not named after the colour brown, it's named after Robert Brown, the same guy who discovered Brownian motion, because this is the type of noise characteristic of a particle moving with Brownian motion. Another way to think about noise and noise colours is in terms of the correlation between two adjacent noise samples. White noise has no correlation at all between adjacent samples. Knowing the previous values of the noise tells you nothing about what the next sample of the noise is going to be. It could be anything. Pink noise, however, there is a correlation between two adjacent samples. If one sample is a particularly low value of noise, the next sample is more likely to be a low value as well. And if one sample has a higher than average value, the next sample is likely to have a higher than average value as well. There is quite a bit of maths behind the correlation of noise, and there's a relationship between the correlation of noise and the frequency spectrum of noise, but that will have to wait for a future course. In terms of what they sound like this. First, Gaussian white noise. And now Gaussian pink noise. And now Gaussian brown noise. And I think it's quite evident that there is a distinct difference in how these colours of noise sound to the human ear. Brown noise, by the way, has a power spectral density proportional to 1 over the square of the frequency. There are other noises, such as blue noise and violet noise, which have more of their energy at higher frequencies, but they are very rare in electronics, so I won't say more about them. That's all I wanted to say this time. Next time we'll look in more detail about why we add the noise powers when we're adding two contributions to noise rather than the noise voltages. There are other noises, including brown noise, by the way, is proportional